In the name of Almighty God, I'm Mahsa Sankoshi, and today I want to talk about surface chemistry using plasma module. Chemical vapor deposition or CVD is a crucial materials processing technique where volatile chemical precursors react or decompose on a heated surface substrate to form high quality solid thin films or microstructures essential for semiconductors, optics, and advanced materials by delivering reactive atoms to the surface while removing gases byproducts. This process offers precise control over film thickness and uniformity, enabling the creation of durable, high-performance coatings for diverse applications from medical implants to electronics. By tailoring the precursors, gases, and energy sources, heat plasmas. And how it works, simplified steps. The first step is vapor introduction. Volatile precursor gases containing the elements for the film are introduced into a reaction chamber. The next step is surface reaction. These gases reach the heated substrate where they break down, decompose, or react chemically. The next step is deposition. The desired solid material forms a thin layer on the substrate surface. The next one is byproduct removal. Volatile, unwanted byproducts are carried away by gas flow. And what are the key advantages? The first advantage is high quality, produces pure, dense, and uniform films. The next one is conformal coatings, excellent at coating complex shapes and internal surfaces. The next advantage is versatility. Works on various materials like metals, ceramics, glass, and polymers. The next advantage is tunable properties, allow customization for hardness, corrosion resistance, and lubrication, and etc. And what are the common energy sources? The first one is thermal CVD, uses heat resistive heaters, lamps. The next one is plasma enhanced CVD, uses plasma radio frequency microwave for lower temperature processing. And what are the applications? The first one is semiconductors, depositing insulators, conductors, and semiconductors for chips. The next one is optic, anti-reflective coating on lenses. The next one and the next application is energy, protective layers on solar cells or fuel cells. The next advantage is biocompatible coating on implants, for example, hydroxyapatite. The next application is tools for hard and wear resistance coating on cutting tools. And what are the challenges? The first challenge is hazardous byproducts, requires careful handling of toxics or explosive waste gases. The next one is cost. Specialized equipment and high purity precursors can be expensive. The next challenge is thermal stress. High heat in thermal CVD can damage sensitive substrates. Chemical vapor deposition. Chemical vapor deposition or CVD is a vacuum deposition method used to produce high quality and high performance solid materials, and the process is often used in semiconductor industry to produce thin films. In typical CVD, the wafer substrate is exposed to one or more volatile precursors which react and or decompose on the substrate surface to produce the desired deposit. Frequently volatile byproducts are also produced, which are removed by gas flow through the reaction chamber. Microfabrication process widely used CVD to deposit materials in various forms, including monocrystalline, polycrystalline, amorphous, and epitaxial. These materials include silicon, dioxide, carbide, nitride, and oxynitride carbon, fiber and nanofibers, nanotubes, and diamond and graphene, and fluorocarbons, filaments, tungsten, titanium, nitride, and various high K dielectric. The term chemical vapor deposition was coined in 1960 by John Blacher or Jr., who intended to differentiate chemical from physical vapor deposition. And what are the types? CVD is practiced in a variety of formats. These processes generally differ in the means by which chemical reactions are initiated. The next is classified by operating conditions. The next is atmospheric pressure, CVD at atmospheric pressure. The next one is low pressure CVD, CVD at subatmospheric pressures. Many journal articles and commercial tools use the term reduced pressure CVD, especially for single wafer tools, in place of LPCVD, which dominates for multi-wafer furnace tube tools. Reduced pressures tend to reduce unwanted gas phase reactions and improve film uniformity across the wafer. The next one is ultra high vacuum CVD. CVD at very low pressure, typically blue, between 10 to 6 Pascal, between 10 to 8 torr. Note that in other fields, a lower division between high and ultra high vacuum is common, often between 10 to 7 Pascal. And subatmospheric CVD, CVD at subatmospheric pressures, usually ethyl and ozone to fill high aspect ratio silicon structures with silicon oxide SiO2. Most modern CVD is either LPCVD or UHV CVD and classified by physical characteristics of vapor. Aerosol assisted CVD, in which the precursors are transported to the substrate by means of liquid gas aerosol, which can be generated ultrasonically. This technique is suitable for use with non-volatile precursors, a direct liquid injection (CVD), in which the precursors are in liquid form, liquid or solid dissolved in a convenient solvent. Liquid solutions are injected in a vaporization chamber towards injectors, typically car injectors. The precursor vapors are then transported to the substrate as in classical CVD. This technique is suitable for use on liquid or solid precursors. High growth rates can be reached using this technique, classified by type of substrate heating. Hot valve CVD, in which the chamber is heated by an external power source and the substrate is heated by radiation from the heated chamber walls. Cold valve CVD, in which only the substrate is directly heated, either by induction or by passing current through the substrate itself or a heater in contact with the substrate. The chamber walls are at room temperature. Plasma method. The next one is microwave plasma assisted CVD. The next one is plasma enhanced CVD that utilize plasma to enhance chemical reaction rates of the precursors. Plasma utilized CVD processing allows the deposition at lower temperatures, which is often critical in the manufacture of semiconductors. The lower temperatures also allow for the deposition of organic coatings such as plasma polymers that have been used for nanoparticle surface functionalization. The next is remote plasma enhanced CVD, similar to PECVD except that the wafer substrate is not directly in the plasma discharge region. Removing the wafer from the plasma region allows processing temperatures down to room temperature. The next one is low energy plasma enhanced chemical vapor deposition or LEPECVD. CVD employing a high density, low energy plasma to obtain epitaxial deposition of semiconductor materials at high rates and low temperatures. The next one is atomic layer CVD, deposit deposit successive layers of different substances to produce layered crystalline films. And the next one is combustion chemical vapor deposition. Combustion chemical vapor deposition or flame pyrolysis is an open atmosphere flame-based technique for depositing high-quality thin film and nanomaterials. The next one is hot filament CVD, also known as catalytic CVD or more commonly initiated CVD. This process uses a hot filament to chemically decompose the source gases. The filament temperature and substrate temperature thus are independently controlled, allowing colder temperatures for better absorption rates at the substrate and higher temperatures necessary for the composition of precursors to free radicals at the filament. Hybrid physical chemical vapor deposition. This process involves both chemical decomposition of precursor gas and vaporization of a solid source. The next one is metal organic chemical vapor deposition. This CVD process is based on metal organic precursors. The next one is a rapid thermal CVD. This CVD process uses heating lamps or other methods to rapidly heat the vapor substrate, heating only the substrate rather than the gas or chamber walls helps reduce unwanted gas phase reactions that can lead to particle formation. Vapor phase epitaxy. The next one is photo-initiated CVD. This process uses UV or ultraviolet light to stimulate chemical reactions. It is similar to plasma processing, given that plasmas are strong emitters of ultraviolet radiation under certain conditions, and PICVD can be operated at or near atmospheric pressure. And the next one is laser chemical vapor deposition. This CVD process uses laser to hit spots or lines on a substrate in semiconductor applications. In MEMS and in fiber production, the lasers are used rapidly to break down the precursors. Gas process temperature can exceed 2000 degrees of centigrade to build up a solid structure in much the same way as laser sintering based three-dimensional speed printers build up solid from powders. And what are the uses? CVD is commonly used to deposit conformal films and augment substrate surfaces in way that more traditional surface modification techniques are not capable of. CVD is extremely useful in the process of atomic layer deposition at depositing extremely thin layers of material. A variety of applications for such film exist. Gallium arsenide is used in some integrated circuits or ICs and photovoltaic devices. Amorphous polysilicon is used in photovoltaic devices. Certain carbides and nitrides confer wear resistance. A polymerization by CVD, perhaps the most versatile of all applications, allows for super thin coating, which possesses some very desirable qualities such as lubricity, hydrophobicity, phobicity, and weather resistance, to name a few. The CVD of metal organic frameworks, a class of crystalline nanoporous material, has recently been demonstrated. Recently scaled up as an integrated cleanroom process, depositing large area substrates. The applications of these films are anticipated in gas sensing and low-K dielectrics. CVD techniques are advantages for membrane coating as well as such as those in desalination or water treatment, as this coating can be sufficiently uniform, conformal, and thin that they don't clog membrane pores. Commercially important materials prepared by CVD polysilicon. Polycrystalline silicon is deposited from trichlorosilane or silanem using the following reactions. For example, SiH color 3 given Si plus color 2 plus H color silicon, H hydrogen 4 which is given silicon plus 2 hydrogen 2. This reaction is usually performed in LPCVD systems with either pure silane feedstock or a solution of silane with 70 to 80% nitrogen. Temperatures between 600 and 650 degrees of centigrade and pressures between 25 and 150 pascal yield a growth rate between 10 and 2 nanometer per minute. An alternative process uses a hydrogen-based solution. The hydrogen reduces the growth rate, but the temperature is raised to 850 or even 1050 degrees of centigrade to compensate. Polysilicon may be ground directly with doping if gases such as phosphine, arsine, or diborane are added to the CVD chamber. Diborane increases the growth rate, but arsine and phosphine decrease it. And what about the silicon dioxide? Silicon dioxide, usually called simply oxide in the semiconductor industry, may be deposited by several different processes. Common source gases include silane and oxygen, dichlorosilane, and nitrous oxide, or tetraethyl ethyl and these reactions byproducts given the specific production, and the choice of source gas depends on the thermal stability of the substrate. For instance, aluminum is sensitive to high temperature. Silane deposits between 300 and 500 degrees of centigrade. Decolorosilane at around 900 degrees of centigrade, and Theos between 650 and 750 degrees of centigrade, resulting in a layer of low temperature oxide. However, silane produces a lower quality oxide than the other methods, lower dielectric strength, for instance, and it deposits non-conformally. Any of these reactions may be used in LPCVD, but the silane reaction is also done in APCVD. CVD oxide invariably has lower quality than thermal oxide, but thermal oxidation can only be used in the earliest stage of IC manufacture. Oxide may also be ground with impurities, alloying or doping. This may have two purposes. During further process steps that happen at high temperature, the impurities may diffuse from the oxide into agents layers, most notably silicon, and dope them. Oxides containing between 5 to 15% impurities by mass are often used for this purpose. In addition, silicon oxide alloyed with phosphorus pentoxide can be used to smooth out uneven surface. Pea glass softens and reflows at temperature above 1000 degrees of centigrade. This process requires a phosphorus concentration of at least 6%, but concentrations above 8% can corrode aluminum. Phosphorus is deposited from phosphine gas and oxygen. Gases containing both boron and phosphorus undergo viscous flow at lower temperatures. Around 850 degrees of centigrade is achievable with gases containing around 5 weight percent of both constituents. But stability in air can be difficult to achieve. Phosphorus oxide in high concentrations interacts with ambient moisture to produce phosphoric acid. Crystals of BPO4 can also precipitate from the flowing glass and on cooling. These crystals are not readily etched in the standard reactive plasmas used to pattern oxides and will result in circuit defects in integrated circuit manufacturing. Besides these intentional impurities, CVD oxide may contain byproducts of the deposition. TOS produces a relatively pure oxide, whereas Silane introduces hydrogen impurities and dichlorosilane introduces chlorine. Lower temperature deposition of silicon oxide and doped glass from TOS using ozone rather than oxygen has also been explored between 250 to 500 degrees of centigrade. Ozone glasses have excellent conformality but tend to be hygroscopic, that is, they absorb water from the air due to the incorporation of silanol in the glass. Infrared spectroscopy as mechanical strain as a function of temperature are valuable diagnostic tool for diagnosing such problems. Silicon nitride. Silicon nitride is often used as an insulator and chemical barrier in manufacturing ICs. The following two reactions deposit silicon nitride from the gas phases. Silicon nitride deposited by LPCVD contains up to 8% hydrogen. It also experiences strong tensile stress, which may crack films thicker than 200 nanometer. However, it has higher resistivity and dielectric strength than most insulators commonly available in microfabrication. Another two reactions may be used in plasma to deposit. These films have much less tensile stress but worse electrical properties. Resistivity 106 to 1015 ohm centimeter, and the electric strength is between 1 to 5 microvolt per centimeter. Titanium nitride. Titanium nitride is commonly used as a wear-resistant coating to increase the lifetime of cutting tools due to its hardness and chemical resistance. Common gas mixture used for depositing titanium nitride with CVD and other gas mixture used to deposit titanium nitride with CVD includes the specific formulation. And what about the metals? Tungsten CVD used for forming conductive contacts, wires, and plugs on a semiconductor device is achieved from tungsten hexafluoride WF6, which may be deposited into two ways. Other metals, notably aluminum and copper, can be deposited by CVD. Also, as of 2010, commercially cost-effective CVD for copper didn't exist. Although volatile sources exist, such as copper, hydrogen, fabric, FAC2. Copper is typically deposited by electroplating. Aluminum can be deposited from three isobutylene aluminum and related organoaluminum compounds. CVD for Molybdenum, tantalum, and titanium nickel is widely used. These metals can form useful silicide when deposited onto silicon. MO, Tau, and titanium are deposited by LPCVD from their pentachlorides. Nickel, molybdenum, and tungsten can be deposited at low temperatures from their carbonyl precursors. In general, for an arbitrary metal, the chloride deposition reaction is as uh, follows. For example, 2MCl5 plus 2 hydrogen, which is given 2M plus 10 H color. Whereas the carbonyl decomposition reaction can happen spontaneously under thermal treatment or acoustic cavitation and is as follows: MCON, which is given M plus NCO. The decomposition of metal carbonyls is often violently precipitated by moisture or air, where oxygen reacts with the metal precursor to form metal or metal oxide along with carbon oxide. Niobium oxide layers can be produced by the thermal decomposition of niobium oxides with the loss of diethyl ether. According to the equation, 2NbOC2H5, which is given Nb2O5 plus 5 C2H5OC2H5. And what about the graphene? Many variations of CVD can be utilized to synthesize graphene, although many advancements have been made. The processes listed below are not commercially viable yet. And carbon source, the most popular carbon source that is used to produce graphene is mm, methane gas. One of the less popular choices is petroleum asphalt, notable for being inexpensive but more difficult to work with. Although methane is the most popular carbon source, hydrogen is required during the preparation process to promote carbon decomposition on the substrate. If the flow ratio of methane and hydrogen are not appropriate, it will cause undesirable results. During the growth of graphene, the role of a methane is to provide a carbon source. The role of hydrogen is to provide hydrogen atoms to corrode amorphous and improve the quality of graphene. But excessive hydrogen atoms can also corrode graphene. As a result, the integrity of the crystal lattice is destroyed and the quality of graphene is deteriorated. Therefore, by optimizing the flow rate of methane and hydrogen gases in the growth process, the quality of graphene can be improved. And use of catalyst. The use of catalyst is viable in changing the physical process of graphene production. Notable examples include iron nanoparticles, nickel foam, and gallium vapor. These catalysts can either be used in during graphene buildup, and surface chemistry is often an overlooked aspect of reactive flow modeling. This tutorial model shows how surface reactions and species can be added to study processes like chemical vapor deposition. The tutorial then models silicon growth on a wafer initially. The example uses a global model to investigate a broad region of parameters with complex chemistry. Then a space-dependent model is set up and run. Careful attention is paid to the overall mass balance in the system, while the difference between the mass averaged velocity and diffusion velocity is explored. The model demonstrates that the total mass and molar concentration in the system is conserved. Finally, the height of the deposited silicon is studied as a function of time. Surface chemistry is often the most important and most overlooked aspect of reacting fluid modeling. Surface rate expressions can be hard to find or not even exist at all. Often it is preferable to use sticking coefficients to describe surface reactions because they can be estimated intuitively. Model definition: this simulation model simulates outgassing from a vapor during a chemical vapor deposition (CVD) process. Careful attention is paid to the overall mass balance in the system, and the difference between the mass average velocity and diffusion velocity is explored. The same physical problem is investigated first with a global volume average model and after with a space-dependent model. An initial study of a problem with a global model is a good approach when there is limited knowledge about the system. One reason is that the global model has reduced computational times, allowing for fast sweeps over parametric spaces. The fast computational time of global models is also a great advantage to investigate models with complex chemistries. In some cases, a volume average model might even be good enough to extract desired information from the model. If, however, space-dependent information is necessary, a space-dependent model can be implemented in a subsequent study. The geometry and operating principle for the model is shown in this simulation. The first one is initially the closed container is full of 99.9% silicon hybrid and 0.1% hydrogen measured by molar content. A surface reaction begins to happen on the wafer, which consumes the silicon hybrid, releases hydrogen onto the domain, alters the composition of the absorbed species on the wafer surface, and deposits bulk silicon. The following reactions are considered on the surface of the wafer. Here denotes surface species, which means that the species only exist on the surfaces where the reaction is happening. To indicate that a species is bulk, append to the end of the species, since bulk species cannot participate in surface reactions. They must only be products and not reactants in a surface reaction. The net result of these two competing reactions is a silicon hydrogen 4 which is given silicon B plus 2 hydrogen 2, which means that it is expected that the silane is replaced by hydrogen inside the reactor and layers of silicon deposited on the wafer surface. Global model equations. The global model used in this simulation considers that the spatial formation of the different quantities in the plasma reactors can be treated as uniform. Without the spatial derivatives, the numerical solution of the equation sets becomes considerably simpler and the computational time is reduced. For detailed information on the global model, see theory for the heavy species transport interface in the plasma module user's guide. In this section, both space-dependent and global model results are presented and discussed. For this particular physical system, the results from the global model and the space-dependent model are in a very good agreement. The y component of the mass average velocity is plotted in this simulation. The mass average velocity is negative at the surface of the wafer. This means that overall mass is leaving the system. This is to be expected since silane is being consumed, which has a molecular weight of 0.032 kg per mole, and replacing it with hydrogen, which has a lower molecular weight of 0.002 kg per mole. From the net reaction, silicon hydrogen 4, which is given silicon plus 2 hydrogen 2, there should be a molar inflow of hydrogen at twice the rate that silane is leaving. Although this condition is not applied explicitly, It is implicit from the equations solved in the heavy species transport interface. Despite the fact that there is a negative mass average velocity, there is a positive diffusion velocity for the hydrogen at the wafer surface. The Y component of the diffusion velocity for hydrogen is plotted in here, and this simulation plots the integrated pressure in the reactor divided by the initial average pressure in the reactor. Once the problem reaches the steady state, the average pressure in the reactor has increased by a factor of 2. This is expected since every mole of silane is being replaced by 2 moles of hydrogen. The silane in the reactor is completely consumed after around 200 seconds. The next figures in this simulation, the total mass initially present in the reactor divided by the total mass in the reactor is plotted. The total mass in the reactor drops by a factor of 8, which is expected since the silane with a molecular mass 0.032 kg per molar is replaced with 2 moles of hydrogen, which has a molecular weight of 0.002 is equal to 0.004 kilogram per molar. Another way of verifying the correctness of the model is to compare the mass lost inside the reactors to the mass accumulated on the wafer surface. The two quantities should be equal. The total gain in mass from surface and bulk species is compared to the total loss in mass from the reactors. The two curves agreed very well, indicating that the total mass in the entire system is conserved. The ultimate goal of most CVD model is to determine the total growth height and growth rate on the surface of the wafer. The total growth height is plotted in this simulation and saturates is at about 159 angstroms. The total growth rate saturates because all the silane in the reactor is consumed after around 200 seconds. The accumulated growth height is also very uniform across the surface of the wafer. The global model and space-dependent model results for the total growth height agrees very well. This simulation is the use of catalyst is viable in changing the physical process of graphene production. Notable examples include iron nanoparticles, nickel foam, and gallium vapor. These catalysts can either be used in situation during graphene buildup or situated at some distance away at the deposition area. Some catalysts require another step to remove them from the sample material. The direct growth of high-quality, large single crystalline domains of graphene on a dielectric substrate is of vital importance for applications in electronics and optoelectronics, and combining the advantage of both catalyst CVD and the ultra-flat dielectric substrate gaseous catalyst assisted CVD. And here we are, we have a components with a specific geometry as a surface. There is a two-dimensional square, and we have used three different physical modules as a heavy species transport. And you can see that we have a silicon hydrogen 4 hydrogen and silicon separately, and also after species we have a surface reaction a species and surface species, and finally we have a heavy species model, and then we have used laminar flow with fluid properties. We had heat transfer, and after all we have average pressure divided by average initial pressure, that you can see that average pressure is being decreased and density ratio and total reactor mass. You can see after a while the total mass density is fixed. Parametric extrusion, accumulated gross height, mole fraction, velocity, pressure, temperature, and diffusion velocity, hydrogen, and also parametric extrusion. Thank you so much for watching my tutorial video until the end, and also you can download this tutorial video from my YouTube, and this computer simulation as surface chemistry tutorial from github.com/mathscript.